Hi, I'll be proving proof 12.2. This proof asks us to prove two different things. The first is to show that if we have some x sub 0, which is an extremum, it must be the case that when we evaluate our derivative matrix at that point, it's equal to the 0 vector. And second, that if we have some manifold and we have a local extremum on that manifold, that we then have the case that the tangent space is a subset of the kern, or a subspace of the kern of D of little f evaluated at that point. So I'll go through each of these in turn. Just the setup is that we have some U open set in Rn, and we have this little f function which goes from U to R, the real numbers, which is a C1 function, so that means it is everywhere differentiable on U. Okay, so the first part that we need to go through is to show that if x is a local extremum of gx, and we also need to make this assumption that the derivative of g prime of x exists, then if this is an extremum at x0, it has to be the case that the derivative evaluated at that point is equal to 0. So that's just a single variable calculus result. So in this case, we're going to define our function g of t as being equal to f evaluated at x sub 0 plus t times some basis vector, or some elementary basis vector. So this is basically just a special case of this function, because this function, we could be looking at it, we could have a whole bunch of different vectors approaching x 0, but in this case we're only going to be looking at it approaching from the e sub I basis vector. So since f is a C1 function, it's also the case that g2 is differentiable, and that's just because, this is basically just the partial derivative, the ith partial derivative, and since it's a C1 function, the ith partial derivative has to exist at x sub 0. So, and more generally by the chain rule, we have that the derivative of g with respect to t is equal to the derivative of this function with respect to t. So derivative of the outside times the derivative of the inside, and t times e of I, the derivative of that is just equal to e of I, the ith elementary vector. And so we know that since x sub 0 is an extremum of f, it's also an extremum of g, the derivative evaluated at t equals 0. And so we have to have the case that this holds. So we have that basically just the partial derivative of our f function is equal to 0, and this is the ith partial derivative, but since we didn't specify which derivative it is, this is true for any partial derivative, and so we have the case that our matrix, our derivative matrix, has to equal the 0 vector. So that's the first part. The second part, we're given this point C, and we're told that it's an extremum, a local extremum on this kind of restricted set. So on this manifold, C is the extremum value, and we know that locally C, which we can break up into the n minus k passive variables and the k active variables, it's there is this g function which defines a is equal to g of b, and in the neighborhood, in this u neighborhood, so close to C, we can define any value of x, the n minus k passive variables, as some function of the k active variables. And so we basically can kind of parameterize this and use our active variables to create this parameterization. And now if we substitute in this parameterization, we're essentially left with an unconstrained maximization problem. And so again, we can apply the chain rule. And since we know we are given that g sub, or sorry, actually, you know what? I'm just realizing here that this should say, this is not the y vector here, this is the b vector, because we're given that C is the extremum. So to have this equal to 0, it has to be the case that we're evaluating this at the point C in the in Rn. In the point C in Rn, we can generate that point C by using our point B and using our graph making function. Right, so we have that. So we have this equality holding, and then we showed in class, we showed that basically the image of your parameterization function is equal to the subspace of the tangent at point C, the tangent space at point C. So now if we have, if we take some vector, which is an element of the image, so that means it's also an element of the tangent space evaluated at point C, and that means that we can put it in here, because any vector, if we hit it with this d of g, we get a vector in the image. So we're left with df evaluated at C, which is the same thing as d of f evaluated at our g graph making function evaluated at B is equal to 0. And this implies that this v, which is some arbitrary vector in our tangent space, is in the kern of the d little f evaluated at C.